Caves raise so many interesting questions. When did they form? How old are the stalactites, stalagmites, and other speleothems within them? How fast did those features grow? Although it's easy to think of caves as peaceful refuges isolated from the outside world, many caves have notable deposits of sediments washed in from elsewhere. This makes it easy to wonder how changes in the landscape above have affected caves below. For example, can the ongoing erosion of a river valley affect nearby caves? What about broader shifts in climate at a geologic scale? Answers to some of these questions have emerged from a recently published study on Fitton Cave in the Arkansas Ozarks. This work reveals a cave history dating back more than 2 million years, extending through much of the Ice Age, a time more precisely known as the Pleistocene, when glaciers made multiple advances across the continent, though never as far as Arkansas. The study's results allowed geologists to look for connections between what was going on in the cave and what the broader geologic record says was happening above ground. And the results are pretty cool. For example, pulses of coarse sediment into this Arkansas cave appear to correlate in time with glacial advances into central Missouri. There's also an intriguing potential correlation between certain cave passages, as mapped here, and old river terraces high above the modern Buffalo River, as mapped here. These terraces have both geologic and historical significance in the Buffalo River country. In this video, we're going to do our best to summarize this complex study and its fascinating results in a way that's accessible to viewers. Keep in mind that this content is our own independent take on the Fitton Cave study, and it wasn't developed in collaboration with the authors. We set the stage for this in our last video, where we discussed the geologic and landscape setting of Fitton Cave, and we'd encourage new viewers to check that out first. This is one of the longest videos we've made, but we think this study is worth the time investment for anyone interested in the Ozarks, caves, or just cool geology in general. Fitton Cave is found in northern Arkansas's Boston Mountains, along the upper Buffalo River, within the drainage basin of Cecil Cove. It has over 8 miles of explored passages, the longest known cave in Arkansas. And in this view from the side, you can see there are several levels of passages. There tend to be long, relatively even sections that are connected by shorter, steeper zones. This cave is also known as Beauty Cave because of its spectacular formations, including some especially delicate ones made of gypsum, as shown in this book. There are also some memorable calcite formations within the cave. The massive pillar on the left is the namesake formation for the room containing it, the missile silo. But the cave's aesthetics weren't the primary concern for this study, or maybe it's just that beauty is in the eye of the beholder. Like many caves, this one contains layers of loose sediment deposited within the passages, mostly washed in from above ground. To the geologically minded, these deposits are tantalizingly attractive, as they contain records of the past that are just begging to be interpreted. The study also investigated some speleothems, such as flowstone and stalagmites. These features build up slowly over time as thin layers of mineral deposits, primarily calcite. If you were to look at a horizontal cross-section of a stalagmite, like this broken one from Missouri's Fisher Cave, you'd see concentric circles that look a bit like tree rings. Unlike tree rings, these don't directly relate to annual cycles, but they still preserve records of the past that are ripe for interpretation. Cutting a vertical cross-section through a stalagmite reveals a clearer profile of the layers that built up over time. The study is based on some basic concepts that we'll walk through here, using a diagram that doesn't represent any specific cave, paired with representative photos from Missouri's Fisher Cave, a state park setting that anyone can visit, unlike Fitton Cave, which is closed to the public. In order to develop a cave in the first place, you need appropriate carbonate bedrock like limestone or dolomite. Mildly acidic groundwater can slowly dissolve passages into the rock, developing into a cave over time. Since many caves have connections to the surface, sediments from the outside can be washed in under the right circumstances. These can end up forming nicely layered deposits that, logically, must be younger than the bedrock surface they're resting on. We can't tell the absolute age of these sediments just by looking at them, but we can infer the relative age using basic geologic principles. The ones on the bottom are oldest, and layers get progressively younger going up. But subsequent erosion by water flowing through the cave can carve away parts of the original deposit, revealing these layers. When we see such an exposure within a cave, we can assume that the sediments once continued laterally before a later channel was eroded. And finally, it's possible to find calcite speleothems developed on top of a sediment deposit, meaning that the cave deposit has to be younger than the sediments it's sitting on. But there are lots of possible permutations that this diagram doesn't show. In this example from Fisher Cave, the flowstone once draped over a sediment deposit that has since eroded away, leaving the speleothem dangling in midair. And in this example from Fitton Cave, multiple flowstone layers are interbedded with sediment. But the standard idea of age progression still applies, with the oldest layers at the bottom and the youngest at the top. But this doesn't tell us when things happened. For example, were these sediments deposited 20,000 years ago, 200,000 years ago, or 2 million years ago? How long did it take for these speleothems to develop? For answers like that, we need to determine absolute dates, and that requires some pretty interesting and specialized techniques. The researchers used 4 different techniques to provide constraints on the age and timing of deposits within the cave, letting different strengths and weaknesses play off each other to tell a more complete story, while cross-checking to see if the collective results are consistent. One downside, it means that we could get really bogged down in explaining methodological details while our viewership crashes. So here we're going to give a super condensed overview of these really cool techniques. We'll start with cosmogenic nuclide burial dating. When quartz sits at or near the Earth's surface, it acts as a dosimeter, accumulating tiny amounts of beryllium-10 and aluminum-26 as a result of cosmic ray bombardment. Thus, they're called cosmogenic nuclides. Quartz in an exposed sandstone outcrop, such as this one in the Cecil Creek Basin, can have beryllium-10 and aluminum-26 build up over time. And these nuclides contain information about how long the rock has been exposed. When pieces of that rock erode and start to travel down through the basin, they carry that beryllium-10 and aluminum-26 with them, accumulating more cosmogenic nuclides on their travels, as long as they remain near the surface. But if they wash into a cave beyond the reach of cosmic rays, then production stops. Beryllium-10 and aluminum-26 are both radioactive, but they have different decay rates. This provides a basis for being able to figure out how long ago that burial happened. This study applied cosmogenic nuclide burial dating to gravel-sized pieces of sandstone found in sediment deposits within the cave. A reasonable assumption here is that the sediments sampled are composed of material that got washed into the cave from above-ground areas of the Cecil Creek Basin. Optically stimulated luminescence, or OSL dating, is another technique for determining how long it's been since sediment was at the surface. The details are more complicated than we want to go into here, but the simplest way to summarize this technique is that it measures the time that has passed since sediment was last exposed to light. So, like the cosmogenic nuclide technique, it essentially lets you determine when material was washed into the cave. This study applied a version of the method called thermally transferred OSL dating to quartz sand found in sediment deposits within the cave. A third method is Uranium-series disequilibrium dating. As we mentioned before, speleothems build up slowly over time as thin layers of mineral deposits, primarily calcite, and these layers can be dated. In short, trace amounts of uranium are incorporated into calcite when it's deposited. Known rates of radioactive decay provide a means of calculating how long ago a particular speleothem layer was formed, though the method is a little more complex than measuring a single decay product. This method works best for deposits younger than about 500,000 years old. The fourth technique is Paleomagnetism. Today, Earth's magnetic field causes compasses to point north, known as normal polarity. But the global magnetic field is also known to have reversed its polarity during different periods of Earth history, such that compasses would have pointed the other direction. We know the timing of these global reversals from broader geologic research. For example, here's part of a figure from this paper, charting these known changes over the last few million years. Here, black indicates normal polarity and white indicates reversed polarity. Certain sediment deposits can lock in a record of the magnetic field's orientation at the time of deposition, providing a framework for age interpretation. For example, the last polarity flip was somewhere between 770,000 and 780,000 years ago, when the magnetic field went from reversed to normal and has been essentially stable ever since. So any sample in the cave that preserves a reversed polarity must be older than at least 770,000 years ago, while a normal polarity sample could be younger than that, or could be from one of the earlier periods of normal polarity. This method doesn't provide an outright age, but it does provide a useful constraint. We hope our magnetic personalities are keeping you oriented toward our content. We're grateful to viewers who have supported us financially via Ko-fi, link below, and for all those who like, comment, and subscribe. With your bedrock support, we can keep delving deeper into Ozark geology. Let's finally look at some results. We're going to focus on one location within the cave as an example, to see how results from different techniques come together. This photo shows parts of a sediment deposit sampled in an area known as the Double Drop Pit Passage. We're going to bring in a cross-section of the same area from a different figure. Note that the vertical scales here aren't quite the same. At the base of the photo is a thick sequence of clay, part of which is obscured by a cave breakdown, meaning some part of the ceiling collapsed at some point. Above the breakdown area is a lens of fine gravel within the clay. Cosmogenic dating returned a burial age of around 1.4 million years for this material. Above that, one layer of clay returned a well-defined reverse magnetic polarity. This means that the clay at this level must be older than around 770,000 years. On top of this entire sedimentary sequence is a flowstone deposit, which logically had to have grown there after all the sediments had been deposited. Uranium dating of this feature was conducted on a set of samples designated FC8, returning what the authors describe as an error-weighted mean age of roughly 610,000 years. This sample pushes the age limits of this technique, so it's best to think of this as a rough ballpark figure. So far, these results are consistent with our expectations based on relative age, older toward the bottom and younger at the top. Now, there is something slightly awkward here, because the cross-section figure labels this feature with a mean sample age of roughly 666,000 years. This value actually applies to a different set of samples, FC6, from a different speleothem in a nearby part of this passage. So as far as we can tell, the value shown here on the cross-section should be 610. This 610 versus 666 issue really shows that when it comes to science, the devil is in the details. But the 666 number is still relevant as a comparable age for a nearby speleothem. We just don't have a direct correlation with this sedimentary sequence. And it's still consistent with the relative age profile seen here. But wait, there is more! The base of this sequence, below the base of the photo, is a deposit of sand and fine gravel. Cosmogenic dating gave the basal gravel a burial age of about 2.2 million years ago. OSL dating on sand from the same level returned a burial age of around 740,000 years ago. But for reasons more complex than we can go into here, this should be considered a minimum age with no implication for how much older it might be. And that allows the OSL sand result to be consistent with the cosmogenic gravel result. So a really cool story emerges here. All four of these methods work together to provide a consistent relative and absolute age sequence for deposits in this location. None of the dates contradict one another, and everything gets younger as you go up the sequence. Similarly clean results turned up elsewhere in the cave, though we're not going to review them here. Now let's take a look at the dating results from one of the many stalagmites sampled in the cave. The results shown here are published in a 2023 data release by the same two U.S. Geological Survey lead authors of the 2025 study, which included these data in its analyses. This example was found not too far from a feature called the organ pipe. Don't worry, the researchers only sampled stalagmites that were already broken, in order to avoid doing further damage to a cave that's protected by the National Park Service. This means that the exact source locations are unknown, but they assumed that all pieces originated near the collection sites. In this vertical cross-section, you can see the layers that accumulated as the stalagmite grew taller and wider. We'd expect the lower and innermost layers to give the oldest values, and they should get progressively younger upward and outward. Sure enough, the oldest value is about 280,000 years, and the values get progressively younger as you go up. The final date, taken right from this piece's tip, came out far older than any other sample. It's fair to assume that something else is going on here, given the consistency of the other results, so this result can be discarded as an anomaly. Also, close examination of these layers shows that the growth rate wasn't steady. For the first part of this stalagmite's life, it grew relatively slowly, at about 6.5 millimeters per thousand years. That's about the thickness of 4 quarters. Then, after a geologically short hiatus, it started growing a lot more rapidly, at 22 millimeters per thousand years. That's about the diameter of a quarter. Yeah, only a geologist would describe 22 millimeters per thousand years as a lot more rapidly. This one piece of stalagmite took over 30,000 years to develop. Even on its own, that's a fascinating insight into cave history. But the really interesting part is how such results tie into the broader geologic story we're about to discuss. The Fitton Cave study assembled the results from different methods and samples into a time series graph like this. For the double drop pit passage we've already talked about, they identified 2 pulses of gravel deposition that could be clearly dated using cosmogenic nuclides. They also identified a sand deposit with a minimum age of 740,000 years, though stratigraphically it was down with this older gravel deposit. They identified a clay layer above these layers with a reversed magnetic polarity, giving it a minimum age of 770,000 years. And they sampled a variety of speleothems whose ages clustered up here in the youngest part of the cave's history, mostly post-dating the sediment deposition. But that's just one site. The full study considered collections of samples from 5 other general locations within Fitton Cave, producing this much more complex summary diagram that we're not going to discuss in depth. Instead, we're going to fade out the details and provide our own summary of how the authors interpreted these data. First, we know that the cave passages had to have developed before the earliest dated gravel beds were deposited, around 2.2 million years ago. For various reasons, the researchers concluded that the cave wasn't much older than that. Next, the results showed a long period of sediment deposition within the cave passages, including other gravel beds whose age averages out to around 1.25 million years ago. Following this, a period of erosion began incising into these deposits, starting somewhere between 1 million and 750,000 years ago. Now things get complicated, as during the same period there continued to also be pulses of further deposition, including another datable gravel bed at around 720,000 years ago. Just to add to the complexity, speleothems also started to develop in the cave, with a wide range of ages dating back to nearly 700,000 years ago, but also quite a few much younger examples. This was a complex time in the life of Fitton Cave. It's so cool to be able to tease out cave histories like this, but the really fascinating part of this study relates to how the authors tied this rough timeline into broader trends in the landscape and climate beyond the cave, which we'll talk about next. Here's how the authors summarize this finding in the abstract. Coarse cave sediment pulses correlate to Laurentide glacial tills about 300 kilometers to the north, suggesting climate influence on periglacial sediment production. Let's unpack this statement by revisiting this figure and focusing on the 3 pulses of coarse sediment previously defined. And here are the time frames for glacial advances into Missouri, as defined by known deposits of glacial till. You can clearly see the loose correlation and timing the authors are pointing to. It's always worth remembering that correlation doesn't guarantee causation. But is there a plausible mechanism for a cause-effect relationship here? Glacial ice never reached Arkansas during the Pleistocene, but glacial cycles undoubtedly affected climate and vegetation far beyond the edge of the ice. During the most recent glacial cycle, when ice made it only as far as south as Iowa and parts of Illinois, pollen records suggest that conifers such as spruce were growing in southern Missouri, a southward shift of boreal forests. So what might have been the effects on northern Arkansas earlier in the Pleistocene, when ice reached its maximum southern extent in central Missouri and southern Illinois? Were there still trees like conifers? Or might the conditions have been even harsher, even tundra-like? Imagine the Ozark landscape partially or mostly stripped of vegetation, with limited root systems remaining to hold soil in place, now exposed to especially harsh freeze-thaw cycles and changes in precipitation patterns. Now add in some megafauna trampling around the basin. Would it be any surprise if erosion and debris transport were more active under such conditions? Recall that in our first video, we pointed out that this area is already prone to landslides due to local bedrock and landscape patterns, even under modern conditions. These sure seem like plausible mechanisms for increased landscape erosion and sediment mobilization during peak glacial periods, tying nicely into the rough time correlation with coarse sediment deposits being washed into Fitton Cave. Another really interesting idea is the concept that the geologic record preserved in the underground darkness of caves may shed light on the erosional history of the above-ground landscape. Let's talk through the premise behind this using a conceptual diagram. Here we're looking at a cross-section through a generic river valley. And in a shout out to Myron Cook and his excellent geology channel, we'll put a tree up here to remind you of this. Over time, the meandering river carves out a broader floodplain beyond its channel, onto which river-transported sediment gets deposited. Now, let's fast forward in time. The river has incised a deeper valley and migrated laterally. It's established a new floodplain, but it left behind evidence of its former floodplain, now high above the river on what's known as a terrace. Cecil Cove, home of Fitton Cave, drains into the upper Buffalo River. Geologists have identified and mapped several different terrace levels along the Buffalo. This is a location downstream of Gilbert, in the Middle River, where 4 levels of terraces show up along a single bend. These are classified by age as younger, medial, old, and even older. But keep in mind that, contrary to normal geologic order, older terrace deposits are actually found at higher elevations, since they were incised and deposited at earlier river levels. So if we were to take a rough cross-section along this ridge, we'd see that the oldest QTO2 terrace is actually the highest, with terraces getting younger as you descend toward the modern river. Early settlers in the Ozarks certainly made use of the lower, younger terraces along the modern Buffalo River, but the higher, older terraces are interesting too. During our last visit to this area, we explored some of the QTO1 old terraces that have been mapped along the upper Buffalo River, not far downriver of Cecil Cove's mouth. Despite being high above the river, these tend to appear as gently sloping areas with notably rounded river cobbles that are otherwise out of place on an Ozark hillside. These terraces also had value to early settlers. This now overgrown field is bordered by a stone wall containing river-rounded cobbles, despite being high above the river. Likewise, this upland cemetery sits in a clearing bordered by a pile of river cobbles cleared from its host terrace. It's really fascinating to walk these old upland fields and recognize the geologic history they represent. A few years ago, we visited one of the really old QTO2 terraces along the lower river, and we were awed to see a lingering deposit of river cobbles almost 270 feet above the modern floodplain. So, okay, these terraces are interesting, but what do they have to do with caves? It turns out that the downcutting of rivers can also affect karst development. Let's return to the conceptual diagram to explore an outline of how this could work. Here's our original landscape configuration, but now let's add a line that roughly represents the water table, meaning that below this level, pore space is saturated. It's reasonable to expect that a fair bit of limestone dissolution and cave development would happen near the water table. For example, let's put a passage here. Now let's move forward in time again, after a pulse of incision has dropped the river to its new lower level. This means that the water table will drop too. Development of new cave passages is now focused lower in the landscape. Sediment and speleothems that have accumulated in these cave passages can be used to constrain the timing of such processes. The point here is that above ground and below ground processes are interrelated, raising the potential that dating results from within such caves may also correlate to external landscape features like terraces. And remember that this side view of Fitton Cave shows that several levels of passages have been mapped. Now to return to a broader view of Fitton Cave and the Buffalo River. Prior studies had addressed the age of the younger QTY and QTM terraces, but those older terraces are pretty difficult to date. Let's zoom in on the B part of this figure. This graphs the distance downriver along the Buffalo against elevation above sea level. The black line is the modern river level. Let's bring in a reminder of the different terrace levels sorted vertically by their relative position in the landscape. On the figure, the white squares are instances of relatively young QTM terraces, while the gray dots are instances of older QTO1 terraces, which, not surprisingly, generally plot at higher elevations than the younger QTM terraces. Now, here's what's so cool about this. The authors of the 2025 study plotted the elevation of sediment deposits within certain passages of Fitton Cave onto this graph to see how they compared with terrace elevations. And there's a noticeable overlap. In their own words, dated cave sediments also may correlate with undated older strath terraces preserved at similar heights above the Buffalo River. Since this study established known dates of deposition for these sediments within Fitton Cave, it's possible those dates also roughly apply to the development of the QTO1 terrace level along the Buffalo River, given the potential correlation in elevation, since we've already shown that terraces and cave passages may share a developmental link. So this potentially demonstrates a new way to date these older river terraces along the Buffalo, something that hadn't been achieved in the past. It's absolutely fascinating to us that caves may turn out to contain key information, allowing geologists to better understand and explain the development of the Ozark landscape we see today, particularly during the Pleistocene. As with all good science, this study provides answers to some questions while raising countless more. And we have some questions for our viewers. What questions and comments do you have about the study? Did you like this style of video where we report on and explain a specific paper? Should we follow up on this by going beyond this research, delving into some hand-wavy personal thoughts and even wild speculation about possibly related themes like the effects of beavers or even the Yellowstone caldera? Regardless, we intend to keep delving into the ever-fascinating Ozarks, and we hope you'll subscribe to join us on the journey.